Hello, everyone. My name is Hanna. I'm a professor and researcher at Data Science Tech Institute and at INRIA. And today I'll be presenting my work, which is titled Project Shadow, Symbolic Higher Order Associative Deductive Reasoning on Wikidata using LM Probing. I'll first start by introducing the task on which the work was based. Then I'll talk a little bit more about the data that's been used. Then I'll formalize some definitions that have been key to the research outcomes that have been produced from the work. And after that, I'll discuss our model experimental setup results, and I'll end with some conclusions. In terms of task, the inspiration for this paper was the Language Model Knowledge-Based Construction Challenge, also known as LM-KBC, which was proposed at the International Semantic Web Conference 2024. Formally, this task aims at predicting all the correct object entities in a subject relation object triple or graph using something called LM probing, which means using intrinsic knowledge that already exists in an NLM after its pre-training. From that, we've altered a little bit the questions in order to answer our own research questions. Research question 1. Can LLMs use deductive reasoning capabilities to understand a new task that shares the same dataset they have been trained on to solve another task? And research question 2. How effectively can LLMs use intrinsic knowledge to solve a new task? We will see how to formalize these questions. In terms of datasets, we have used the original dataset made available to us publicly by the LM-KBC task owners. This dataset is a grouping of triples from Wikidata that have the form subject relation object. And in order to control a little bit the original task, the type of relations were limited to 5 big relations: country, land, borders, country, person has city of death, series has number of episodes, award won by, and company trades at the stock exchange. We ended up with 3 types of datasets: a training data set, which contains 377 triples, a validation set, which contains 378 triples, and a final blind test set for the official result submission for the task at hand, which also contained 378 triples. So the 3 given sets were evenly numbered and um, evenly matched in terms of number of triples. Some definitions that inspired our work. So our goal here was to actually go a little bit beyond this task, even though we ended up submitting results to the task itself, but we didn't really stick to just gauging LLMs or probing an LLM in order to evaluate its intrinsic knowledge. We wanted to go beyond that and to see how effectively can an LLM use its intrinsic knowledge in a different set of scenarios, a little bit like what we humans do when we have some set of knowledge and we can apply this set of knowledge in different fields or in different scenarios. So the first big element that we've worked on was associative learning. So associative learning is a concept whereby 2 stimuli become linked or learn in tandem, and the elements of one stimulus become associated with the second stimulus. This was very interesting to us because this was a little bit the reasoning that was behind the idea that we wanted to implement for our LLMs. We wanted to use some key elements of knowledge that the LLM already knew, more specifically on the Wikidata dataset that was the focus for this task, and to see if using this knowledge, the LLM can solve a different kind of task. This brings us to the second element of definition, which is transfer learning. Transfer learning is a key concept in the artificial intelligence field, specifically in deep learning. It's the concept by which we take one pre-trained model on a task and we use the knowledge it has in order to solve another task. So it's a little bit different than associative learning. This is why we've put the 2 concepts here in order to try to combine them and to get the best of both to be able to implement a new strategy for our LLM learning. Finally, this is where we derived a new concept called associative deductive task learning. The idea behind this, as I've said, is to combine the best of both associative learning and transfer learning, meaning designing a new task that the LLM is not aware of, does not know it exists, and the only thing that the LLM can use in order to solve this new task is some existing knowledge that it already learned by solving another task. So this is obviously a hard challenge for an LLM because it requires both associative and deductive reasoning to solve the task. It requires understanding the task and trying to derive some sort of correct solution from existing knowledge. If we want to formalize this, we designed a task whereby we have a set of 5 numbers, which we will refer to as template IDs, that correspond to 5 templates. These templates are actually Sparkle queries, so a set of symbolic reasoning queries that are designed to fetch the knowledge graph completion or the object entities for the respective starting triples of subject and relations that are given to us in our sets. So the Sparkle queries can very well solve most of these knowledge graph completions, and we will discuss a little bit later on why it's most and not all, but they are enough to actually solve the problem or the original task at hand. To make it more interesting, we've put them behind template IDs. Of course, the LLM that we will use, the model that we will leverage, has no idea that there are some Sparkle queries behind our templates. And its real task is to try to pick the best template ID in order to indirectly gain access to the correct query that solves the knowledge graph completion problem for it on the Wikidata sets. Why did we go through the trouble of actually redefining the task? It seems like a lot of work. It seems like we're going around things instead of directly tackling the task. Actually, redefining the task is a kind of problem simplification here because the original task is a task whereby the LLM needs to complete a knowledge graph triple. So this is a generative AI task. And here we have simplified and reduced the problem to a simple classification whereby the LLM needs to choose the best out of 5 classes or template IDs or categories, which are just numbers. The second advantage of redefining this task is that we do not need any additional data. The existing data that we have at hand, as well as the intrinsic knowledge that the LLM already knows, should be sufficient to solve this problem since we are still working on the exact same dataset. Of course, the biggest advantage out of this method is the fact that it now becomes a grounded problem instead of it being an open-ended generative problem where we should worry about controlling the output of the LLM, hallucinations, and transparency of the method. Here, we have solutions to these 3 big pillars. The fact that the Sparkle queries are the real answers grounds the problem logically. We are sure that if there is some bad answer to a triple, it's probably because either the LLM picked the wrong group or template ID, which we can address, of course, or the Sparkle itself is wrong. And here, by introducing the human in the loop factor, we can render the results more explainable and we can ensure that we can fix them in a proper way. And we can, of course, make them more transparent. So the model that we've trained was baptized Shadow. Shadow is an acronym that stands for Symbolic Higher Order Associative Deductive Reasoning on Wikidata. So you can see the big terms that we've defined here in the name. It's a small language model, so it's fine-tuned on a base. Actually, it's fine-tuned on a small T5 model. Why pick T5? Because it's an openly accessible model. It's a model that does well on these kinds of tasks. And the training that we've done by redefining the task was simply to train it on classification, train the LLM on a classification task to predict the best template ID. You can see here in our experimental setup that we've modeled the experiment in the form of a question answering problem with a prompt that asks the LLM what is the best Z that completes the relationship Y for X Z being obviously the object or set of objects in the triple that are missing, X being the subject, Y being the relation. And you can see that Shadow is trained to generate the correct template ID for the correct query given the starting subject and relation of a triple. Of course, without it really knowing that what it's really selecting is a proper query. Any other output that Shadow generates outside the 5 classes is considered incorrect. So this is a way for us to also control the outputs of the model. We've split our training data sets to 80% for training and 20% for validation in order to give our model the best chance of learning. In terms of results, so we've submitted our results to the official LM-KBC task using the redefined problem and making Shadow learn on the problem. And as you can see from our results, specifically in table 2, our model does quite well on most of the results. A small note here with respect to the country land borders country, you can see that in terms of F1 score, it is the worst out of the relations. This is not really directly the LLM's fault. It's mainly the fault of the Sparkle query, which solves this kind of knowledge graph completion by targeting the P47 Wikipedia property, which is actually the country, land, borders, um, which is more open than the country, land, borders, country property that is asked of in the task, which means that it will more likely yield more results than necessary, most of which would be useless for the task at hand. So this is a known, deliberate shortcoming in our setup, but it's a small price to pay in order to be able to verify the task redefinition. The series has number of episodes actually has a perfect precision, zero recall, which suggests a very cautious classification that is being done by the LLM. And this is also interesting, mainly because series has number of episodes is the only relation out of the 5 that expects object results as numbers. So maybe the LLM has some shortcoming in learning this kind of relations or during its pre-training on the original Wikidata dataset. The award won by relation score shows the importance of using intrinsic knowledge and the way that an LLM can use intrinsic knowledge since it scores very well with respect to other relations, noting that in the original dataset given by the organizers, we had 1/10 of data available for this relation with respect to the other relations which were equally balanced. So the fact that with 1/10 of the data, the LLM performed as well on this relation shows that in terms of intrinsic knowledge, this LLM probably has solid knowledge with respect to this relation. In terms of ranking with respect to other models and methodologies, Shadow actually outperforms the organizer's baseline model by a healthy 20%. So this is a method that shows a lot of promise. However, with respect to other models and systems, Shadow falls a long way in the classification or the final scoreboard for the task at hand. So there are limitations to this methodology, most notably in actually tapping and measuring effectively the value and the amount of intrinsic knowledge that the LLM has and the way that it's using it properly. And this will obviously be an open research question for us to work on later. If I want to conclude, in terms of our research questions, where do we stand? In terms of research question 1, it is unclear to what extent an LLM can use reasoning, but we can see that for sure the pattern matching type of reasoning that LLMs work with to navigate a new task using an existing or a familiar data set helps it greatly in order to understand a new task that it has unseen before that requires it to use its existing knowledge. And for question 2, LLMs can effectively leverage previously amassed knowledge to successfully perform well on an unseen task. This was highlighted especially for the award won by relation, where with less data, the LLM was able to consistently perform well. This work opens up new avenues in experimental settings to test LLM reasoning and knowledge probing, and more specifically, to come up with ways or to find ways to better evaluate this kind of use of their internal knowledge. Thank you very much for listening. Please don't hesitate to get in touch for any questions.